So this is the master recurrence relation for divide and conquer algorithms. This one right up here that I've written on the top of the screen. So the way to interpret this is the following. First, let's look at the last term, the f of n. So the f of n captures the amount of effort, or the cost, if you want, associated with the overhead that we have to do to make a recursion happen. So every time we recurse, we incur this much overhead. So this is, we'll just call this the overhead term. Okay? The b is the factor by which we shrink the size of the input each time we recurse. So b here is the reduction factor in input size. Okay, so if b is 2, that means we're cutting the input in half. If b is 5, that means we're cutting the input down to 20% of its original size. And then last, the a, you can think of as the number of recursive calls that need to be made, or perhaps the number of chunks that we break the problem into. So a corresponds to the number of chunks, to use the technical term in divide and conquer. Often this will just be as simple as the number of recursive calls that get made each time we pass through this thing. So we've already seen a couple of these, right? We saw this max find algorithm that I showed a couple of videos ago. We've seen binary search sort of informally. And in binary search, a was 1, right? We have only one recursive call, but we shrink the input by half. And f of n is just a constant 1. In max find, the difference is that a was 2, and b was still 2. So we're still cutting the input in half, which is what b tells us. But then we make 2 recursive calls, which is what a tells us. And then the overhead was still constant time. So the question is, what does this look like in general? And in particular, what happens if we have a more general overhead term? Well, it turns out that it depends on the relationships between these three parameters in some kind of surprisingly precise ways. But before I show you exactly how all this works using the master theorem, it's literally what it's called, is the master theorem, I want to help us gain some intuition by looking at some special cases. So first of all, we can ask, what happens if the overhead term is the most important part of the recurrence relation? And so what does that mean? Well, it basically means that a is small. So our case 1 here will be a is small, and in particular, it is small relative to the overhead term. So relative to overhead. Right? And now you don't know what it means to be small relative to overhead yet. You will, we'll go into the details of this, and you'll be able to see exactly what it means to be small relative to overhead. But suppose we knew that for whatever reason, there's just not that much recursion going on, but there's a lot of overhead. So here's an example of a recurrence relation that actually does have a small a relative to f of n. So the recurrence relation is 2 t of n over 2 plus f of n. Or excuse me, plus not just any f of n, but n cubed. Okay, so what is our a? Well, a is 2. We have 2 recursive calls, right? B is 2. We're cutting the input in half every time. And our f of n is n cubed. So sometimes it's useful to have some intuition about what this recursion would actually look like. And what does it mean actually look like? Well, we can draw a tree, right? Every recursion defines some kind of a decision tree, and we can actually depict that graphically. So picture this being not a graph algorithm, an array algorithm. So you're given an array, you cut it in half, you go process both halves, you cut each of them in half, you process both of those halves, and so on down. What would that actually look like? Well, just the recursion piece looks like this. So we're imagining that the input array has size 8, and it looks like this. Well, what happens is we take the array, we cut it in half, and we recurse on both halves. So then we have 2 arrays of size 4 each. All right, so there's our 2 arrays of size 4. Cut each of those in half. We go process them. And now we have 4 arrays of size 2. And each of them gets cut in half, and we end up with 8 arrays of size 1. So there's 1, 2, 3, 4, 5, 6, 7, 8. And if you don't mind, I'm not going to draw all the brackets. Okay, so what we can do is kind of think about what is the overhead going to look like on each of these terms. First, before we do that, we could think about how many leaves there are, right? So part of what happens in the recursion is you recurse, and then you have to do something at each of the leaves of this recursion tree. So what is a leaf? Well, it's one of these, right? And we can always ask, and should always ask, how many leaves are there? So how many leaves does this tree have? Where a leaf corresponds to one execution of the recursion base case. So, rather than leaves, you can think of, recursion base cases. Okay, well, there's exactly 8, right? There were 8 elements in our input, and now there's 8 size 1 arrays, so there's 8. So in this particular one, there are exactly 8 leaves. Okay, and we can think about how that generalizes, but for this we have 8. So now we see what the recursion does. The recursion goes down several levels and then ends up with a bunch of these size 1 arrays. It turns out exactly as many size 1 arrays as there were elements in the original array, and then it's that's the recursion. That captures everything there is to care about with the recursion. But what about the overhead? So let's think about how much overhead is being done on this algorithm. So first, when we do our first split, there are 8 elements here, right? So we'll say there's n elements, and so there is n cubed amount of overhead done. Okay, and that just comes directly from here. So now on the second level, we have 2 arrays that are each half the size of the original. And so how much overhead gets done down here? Well, 2, right, because there's 2 arrays, times n over 2 cubed. Okay, and so, if we actually want to think about plugging numbers in here, we could do this, and I'm not going to write out 8 cubed, but what we could do is we could say, hey, this is 8 cubed. And then this is 2 times 4 cubed, which I can write that down, right? That's 128, right? And then the next level down, I have 4 arrays that are each n over 4 length, and so we have that much effort cubed. So our size for each array at this level is n divided by 4. And so there are, each of those arrays gets processed and incurs some overhead. In particular, it incurs n over 4 cubed overhead. What is n over 4? Well, that's 2. So now this is going to be 4 times 2 cubed. Well, 2 cubed is 8. So what's 4 times 8? Well, that's 32. And so it continues. And down at the bottom we have 8. Now there's 8 size 1 arrays, and each of those is size n over 8. Whoops. Keep my colors consistent here. Each of these is size n over 8, and we cube that, and so this is exactly 8. So what do we have? Well, I mean, we could try to work out all these numbers and things, but essentially what you see is that no matter what happens down here, this is a huge number, right? This is a costly thing to do. When we first start this thing, no matter what happens afterwards, no matter how much that stuff shrinks, we still have to do 8 cubed, overhead up at the top, whatever this means, right? And notice if the array were larger, that larger number would be cubed. So one question we can ask is how much overhead gets done overall? So our question is, what is the overall overhead? Well, it's this, right? It's n cubed. We know we get n cubed from the first firing of this thing. So it's n cubed plus this thing, right? Plus 2 times n over 2 cubed, plus this thing, 4 times n over 4 cubed, and so on, right? What is this? Well, this goes on for some distance, but notice each one of these has an n cubed in it, right? So this is n cubed times something, right? Who knows what this something is, right? It's something that depends on n, certainly. There's no doubt about that. But whatever this thing is, it can't be, it is a positive number that can't make our n cubed complexity any better, right? And you can see that just by the above, right? You can see that by the fact that the first time this thing recurses, it costs 8 cubed effort, and there's no way to get that back, right? We no matter how fast the rest of the recursions happen, that 8 cubed is always with us. So what we have is, the recursion essentially gives us linear cost, right? The recursion results in a linear number of recursion base cases happening, but the overhead costs at least n cubed effort. Okay, so what does this give us? Well, this doesn't tell us. I have not done enough analysis to tell us exactly what the complexity class is of this thing, but what this tells us is that T of n is in big omega of n cubed, right? No matter how good T of n is, right? No matter what happens, we still are stuck with this n cubed, right? The recursion causes far less complexity, far less effort than that n cubed of effort that it takes to split the very first array. So no matter what happens, we're at best we have an n cubed algorithm for this case. And so notice this n cubed comes directly from the overhead here. So one of the takeaways, one of the intuitions I hope you can take away from this is that if A is small, right, if the number of recursions is small relative to how much overhead happens, then overhead dominates, right? So what do we get? Well, if this is the case, then overhead dominates.